So each year, thousands of pets and wildlife die from consuming antifreeze. And the deal is that most antifreezes contain ethylene glycol, which is an alcohol, and it has a sweet taste, which is what the attraction is. And so if you were to consume ethylene glycol, initially you would get a drunkenness effect, just like you would with any other alcohol. But alcohol gets metabolized by enzymes in the liver, and it gets converted to glycolic acid. Now, why is that an issue? Well, body likes to tightly control pH, and adding extra acid is a problem. So let's take a look at the reasons why. Now, the body has to be able to withstand a great deal of chemical pressures on it. And in the blood has to be able to deal with taking up and delivering products, and that can create shifts in the blood. So the blood has a built-in pH buffering mechanism, and it involves water and carbon dioxide. Now, the blood is mostly plasma, and plasma is mostly water, so that works out really well. What happens when carbon dioxide and water combine is it creates the weak acid known as carbonic acid. And carbonic acid, being an acid, will cast off a hydrogen ion and leave behind a bicarbonate ion. So this is the buffering system in the body. So the body can take up this carbon dioxide and make this weak acid, and it makes the blood a little bit more acidic. But eventually, we're going to get rid of that carbon dioxide, and it'll cause the equilibrium to shift back to the left. So what's happening out in the tissues? This is where we're going to find a lot of carbon dioxide because the cells have used up all the oxygen in their cellular activities, and they're making this byproduct of carbon dioxide. And we know that if we add carbon dioxide to the left side of the equation, that's going to shift the equilibrium to the right. So the presence of carbon dioxide in the blood is going to make the blood a little bit more acidic, but not a lot more acidic, because we have this intermediate, which is carbonic acid, which makes this weak acid. Now, in the lungs, one of the things that's happening is that our blood that's carrying carbon dioxide gets to the lungs, and in the lungs, there's a big pressure difference between carbon dioxide in the blood and carbon dioxide in the lungs. And as a result of this pressure differential, the carbon dioxide in the blood is going to come out of the blood and go into the lungs, and that's going to shift the equation to the left, so it'll make it less acidic as a result. Now, there's another thing that's happening that I haven't talked about yet. So far, I've talked about this buffering system and how it's taking up and eliminating carbon dioxide. But the other thing that's happening is that we have to have a way to effectively bind oxygen. And oxygen in the blood will bind to hemoglobin that's found in red blood cells. And here's our hemoglobin, and here's our oxygen. So in the lungs, what's happening is that the blood is taking up oxygen, and it's therefore driving the reaction to the right and making the blood just a little bit more acidic. So it's this back and forth with the presence of carbon dioxide and the presence of oxygen, maintaining a very tightly controlled range of blood pH. So what then happens after you drink antifreeze? Well, initially, you're going to get that drunkenness because it is an alcohol, but once it's floated around in the blood, it's going to eventually make its way over to the liver, and the liver enzymes will do some work on it, and it's going to turn it into glycolic acid. And if we add glycolic acid to our blood, one of the things that it's going to do is going to shift the buffering system to the left, and it's going to cause carbon dioxide to come out of its bound state as carbonic acid, and it's going to have this carbon dioxide now in the blood. And there are chemoreceptors in the body that will detect this, and it'll send a signal to the brain that tells the brain to engage the respiratory centers and cause you to breathe heavy, because it thinks that this carbon dioxide is building up in the blood, which it is, and needs to be breathed out. That's our quick way of dealing with a buildup of carbon dioxide in the blood. Now, the other thing that's happening that's more detrimental to our tissues has to do with our second equation, because if we add more acid to the blood, one of the other things that's going to happen is it's going to decrease the ability of oxygen to effectively bind to hemoglobin in the blood, because it's going to shift that equation also to the left, and it's going to now mean that oxygen gets released in the bloodstream instead of at the tissues, and now our tissues are starving for oxygen. So this is why taking in glycolic acid is so deadly. It's because of the shifts in pH, and this leads to a condition called acidosis. So under normal conditions, the body can deal with these little shifts in blood pH by using that buffering system. But if we add high enough concentrations of glycolic acid to the bloodstream, it'll overcome the buffering ability of the carbonic acid in the blood and the bicarbonate ions to overcome those drops in blood pH. And this leads to this condition, like I said previously, called acidosis, where you see a decrease in the oxygen binding ability of hemoglobin. So what's the treatment for this? Well, the quick and ready treatment is to actually give the patient alcohol. Give them a shot of tequila. And the reason why this works is because ethyl alcohol, what you'd find in tequila or whiskey or any other alcohol, has a higher binding affinity to the enzyme that catalyzes and metabolizes ethylene glycol. So now you're preferentially breaking down alcohol that your body can tolerate, as opposed to ethylene glycol, which your body can't tolerate in its metabolized state because it makes the body too acidic. Now we just had a quick lesson about buffers. So what then is a buffering solution? Well, it's a solution that can resist changes in pH when either an acid or a base is added to the solution. Now the components of the buffer act to neutralize the effects of the acid or the base once it's added to that solution. And in order for a buffering solution to work, it must contain either significant amounts of a weak acid or its conjugate base. And in the case of the example we saw, our weak acid was carbonic acid, or it has to contain significant amounts of a weak base and its conjugate acid. And the example of the buffering system in nature was that which we saw with our blood, and that had to do with this equation right here. So if we look at this statement, significant amounts of a weak acid, our weak acid is carbonic acid, and its conjugate base, which would be this right there, the bicarbonate ion. For an acidic buffering solution to be effective, it must contain significant amounts of both a weak acid and its conjugate base. And usually the conjugate base gets added, at least in the chemistry lab, to a solution as a salt. So in our example that we see, it's sodium acetate that gets added as the source of the conjugate base, which is the acetate ion. So what happens to a buffer solution when a small amount of a strong base is added to it? Well, if the strong base is added, then the base will be neutralized by the weak acid component of our buffer. So let's take a look at an equation. So here we have sodium hydroxide and our weak acid, vinegar, also known as acetic acid. And if we combine those two, we're going to end up with water and sodium acetate. So we can see we have a 1-to-1 ratio here, which will give us a 1-to-1 ratio with our products. So if we add 1 mole of sodium hydroxide to 1 mole of acetic acid, then we're going to get a complete neutralization, and we'll end up with 1 mole of water and 1 mole of sodium acetate. But what happens if we were to double the amount of sodium hydroxide? Well, only half of it would be neutralized, and we would end up with about 1 mole of sodium hydroxide left in our container. And this is going to have a little bit of an effect on the pH. Not a big one, but a little bit of an effect. So what we would find is that the pH of our solution would change a little bit, maybe with a slight increase, or maybe not at all, depending upon how much we added. But I'm giving you an example where I'm showing you explicitly as long as we have enough acetic acid to neutralize our base, we're going to end up with no changes. Once we see a significant amount of base being added, that we're going to see an increase in our pH. So then it would hopefully make sense that if you added significantly less of a base to a buffering solution, that the amount would have virtually no effect on pH. You probably wouldn't see any changes because if you added, let's say, half a mole of sodium hydroxide, all of that would be neutralized and it would have no effect on the pH. And so you'd end up basically having left over water, sodium acetate, some sodium acetate, but then you'd have some leftover vinegar as well, which would basically not change your pH at all. So then what would happen if you added a little bit of a strong acid? Well, the same thing. If you add the acid, then it's going to be neutralized by the conjugate base component of the solution. So let's take a look at that reaction. So here we have our strong acid, hydrochloric acid, and now it's going to act with sodium acetate. So this acetate ion, this is a negatively charged ion hanging out with a positively charged sodium, is now going to be the receiver of our H from hydrochloric acid. And as a result, we're going to create a little bit of acetic acid and some spectator ion right here. So then what we conclude is that the pH of the buffer will change maybe a little bit. You might see a slight decrease as more of our acid is made, or maybe you won't see one at all. It really depends upon how much of our acid that we make. And if we add significantly less acid, then the amount of pH change will be very, very small as a result of that. So we can take a look also at how Le Chatelier's principle is at work here. Now, with our acidic buffering solution, remember we have a weak acid and its conjugate base, which is going to be that negatively charged ion. And for an acidic buffering solution, if we add a base to it, then it's going to be the weak acid that will react to neutralize it. And if we add an acid to our acidic buffering solution, it's going to be the conjugate base that react to neutralize it. Now we can't forget the role of the hydronium ions, because remember hydronium ions are where that positively charged hydrogen ion hangs out until we use it somewhere, like here or here. And what happens with those is that by the time the equilibrium is established, the concentrations of those hydronium ions will be kept constant. And so it becomes the measurement of these hydronium ions that will tell us the pH. So we've established that this is what happens. This is the relationship between our weak acid and its conjugate base. Now the conjugate base could also be called the common ion or the conjugate base. And we can see that it's on the right side of our equation with our hydronium ions. Now when we're measuring pH, we're measuring the amount of hydronium ions present, not necessarily the amount of our weak acid. We measure the hydronium ions. So keeping that in mind and keeping in mind what a common ion is, let's proceed with this slide. So by adding a salt, which is going to be our common ion, the effect that it has is to shift the equilibrium to the left. Now that means we're going to be shifting the arrow to the left, and we're going to be making more water and more of our weak acid. Now what's that going to do to the pH? Well, we're actually going to see that the pH gets to be higher. It becomes more alkaline as a result, because we're going to see less of these present, less of the hydroniums present in solution. So as we add more of this, our hydronium ions get converted back into water molecules and weak acid, which means that fewer of these hydronium ions available, the less acidic our solution. Oh, how do we calculate pH? Let me count the ways. Well, certainly we could use the Henderson-Hasselbalch equation, but before we launch into that, let's remind ourselves that we used a formula very similar to this previously to calculate pH, where we looked at the concentration of hydronium ions which tells us about the concentration of hydrogen ions. Now, with the Henderson-Hasselbalch equation, we're now taking into consideration the pKa, where Ka tells us about the acid dissociation constant of our weak acid. Now, this holds true for weak acids, not necessarily for strong acids, because remember what we're trying to do here is measure the pH of our buffering solution. The way we got to pKa is we used this equation right here, very much like what we used to calculate our pH. All right, so the Henderson-Hasselbalch equation then is derived from the acid dissociation constant of our weak acid. It's another way for us to calculate our pH, specifically to a buffering solution. And the equation calculates the pH of a buffer by using the pKa, the potential acid dissociation, and the initial concentrations of the weak acid and the salt of the conjugate base. And this only holds true if the X from our hydratic equation approximation is true. So X has to be small in order for us to use the Henderson-Hasselbalch equation. So how do we get to the Henderson-Hasselbalch equation? Well, we start off with our basic equation where we have our weak acid in water and it creates our conjugate base and hydronium ions. And we're going to solve for the concentration of hydronium ions. And we set up our equation like this. So we have our acid dissociation constant, and that fits in with our value of K. That's how we figure out K. And then we can rearrange that and isolate the concentration of hydronium ions, which gives us this value right here. Now we're going to take the logarithm of both sides, and then we're going to expand out this logarithm right here. So here we've taken the log of both sides. So we've taken the negative log of the concentration of hydronium ions and the negative log of Ka over our acid and our conjugate base concentrations. And then we're going to expand out the log of this expression right here. So we end up with this expression at this point. So we're getting close. So what else do we have to do? Well, let's look on the next slide. So this is what we had from the previous slide. So what we're going to do next is we're going to multiply both sides by -1 and rearrange so that we get the following equation. So what's basically changed here is that we now have flipped what's in this expression. So HA was previously on top and now it's on the bottom. And next what we're going to do is this. Since pH equals the negative log of the concentration of hydronium ions and pKa equals the negative log of the acid dissociation constant, and we happen to have both of those values right here, we can now do a substitution for this. So we have pH is equal to pKa plus the log of our concentration of conjugate base over our weak acid. And furthermore, we can generalize it like this. So that's how we end up getting the Henderson-Hasselbalch equation. So how do you solve for the pH of a buffer solution? Do you use an ice table or do you use the Henderson-Hasselbalch equation? Well, you can use the ice table for under all conditions. You can use this to solve for the pH of a buffering solution always. You can always do that. You could use the Henderson-Hasselbalch equation if X is small. So if that X is small approximation holds true, then you can use this one, which means that in order to determine if X is small, the initial concentrations of the acid and the salt are not very dilute, and your acid dissociation constant is fairly small. So as long as these two are in place, then you can use Henderson-Hasselbalch instead of the ice table. The other thing to keep in mind is that for most problems, this means that the initial acid and salt concentrations should be over 100 to 1,000 times larger than the acid dissociation constant. So these are the requirements in order to use Henderson-Hasselbalch. So when you add an acid or a base to a buffering solution, what happens to the pH? Well, ideally, the buffering solution is going to keep that pH really close to where it was, because remember the whole purpose of a buffering solution is to resist big changes in pH. So what's happening here is that, let's say you're going to introduce a little bit of acid to your buffering solution. And we have a buffering solution here that's made up of our acid, our weak acid, and the conjugate base. And then, of course, it's in water, so I have some water molecules here too. So if we drop this acid into our buffering solution, what will happen is that these will preferentially couple up with the conjugate base, and as a result it'll make a little bit more of our weak acid. Now this really hasn't changed our pH much, if at all. And we might even add a little bit more acid to our buffering solution and make a little bit more of our weak acid. Maybe not even much of a pH change at this point. But what if we were to overcome all of the conjugate base present in our buffering solution, and we added just one more little bit of acid? Well, now this acid has no other conjugate base to couple with, so now it's going to find a water molecule and it's going to make a hydronium ion. And this is the point at which we're going to see an increase in our acidity, or rather a decrease in our pH. So this is the concept behind what a buffering solution is actually doing for us. So every time we were to make a shift, you would see it. You would see the acid preferentially combining with that conjugate base in order to resist those pH changes. And it's not until you get to the point where what you're adding to the solution overcomes the amount of buffer present that you're going to see those big swings starting to happen in pH. So like I said, the pH of a buffering solution is going to remain relatively the same, or maybe even only slightly changed, as long as there's sufficient amount of each of the buffer components, as long as there's sufficient amounts of the weak acid and its conjugate base, or a weak base and its conjugate acid. Depends upon what sort of solution you're working with. So how do you determine the pH of a buffering solution after you've added something to it? Well, it's a two-part process, and the first one involves a stoichiometry calculation for the reaction. And you have to keep in mind that the added acids are going to react to reduce the conjugate base but make more of your weak acid. And if you were to be adding base, we didn't really talk about this, but if you're to be adding a base, it would react with your weak acid to make more of your conjugate base. So this sounds very much like an ice table, where you would be plugging in these amounts and then figuring out the changes that occurred in order to get your new calculations. Then the next thing you would need to do is do an equilibrium calculation using the values, your new values of your weak acid and your conjugate base. So up until this point, we've been looking at buffers as being weak acids and their conjugate base. And it is entirely possible to make a basic buffer. And the way we would do that is we would have our weak base in our water, and it would create a weak acid and some hydroxide ions. So here's our base, and the way we would make our weak conjugate acid would be to take and add a chlorine ion to it, as well as a hydrogen ion. That's how we would get that positive right there. So, for example, we could take ammonia and ammonium chloride, and ammonia would be our weak base, and ammonium chloride would be our conjugate acid salt. And the equation for this would look like this, where we have water and ammonium, and we're going to have the reversible reaction where it creates ammonium ions and our hydroxide ions. Well, can we use the Henderson-Hasselbalch equation for basic buffers? Well, yes, we can, but we have to do a little bit of tweaking. So the Henderson-Hasselbalch equation is written for a chemical reaction with a weak acid and its conjugate base as the product. So that means that we're going to have to rearrange what we've got going on to fit this. So let's see how we're going to do that. All right, so the chemical equation for a basic buffer is written with the weak base as a reactant and its conjugate acid as a product. And that's the opposite of what we do when we're dealing with an acidic buffer. So this is what our equation for our basic buffer looks like. So here's our base, our weak base, and then here's our conjugate acid. And if we were to come up with the dissociation I'll get it out. constant, or we might even think of this as the equilibrium constant, then we could see that we're going to be putting our base in the top, and our actually take that back, our base is in the bottom and our acid is in the top of this equation. And this would be true. The dissociation constant for this would be true for this base. But to apply the Henderson-Hasselbalch equation, the chemical reaction of the buffer, basic buffer, has to be more like the acidic reaction. And the way that we achieve that is by reversing the reaction. So in this first reaction, we have the base as a reactant and its conjugate acid as a product. But in order to apply the Henderson-Hasselbalch, we now have to put the conjugate acid as the reactant and the base as product. And then that will allow us to plug in to get the K of A, which we need for the Henderson-Hasselbalch equation. So if we look at K of A, we can now see that our base is on the top and our conjugate acid is in the bottom. And now we can actually plug this new value in our equation. So here we're going to find the pH, and we're going to do the pKa. And we're going to write plus the log of our base plus the conjugate acid. So as we just saw, there is a relationship between the dissociation constant of a weak acid and the dissociation constant of its conjugate base. And there's also a relationship between the pKa, or the power of the ionization of the acid, or the ionization constant of this weak acid, and the power of the conjugate base. So let's take a look at that. So if we were to put the dissociation constant of our acids and its conjugate base into an equation, what we would get is the dissociation constant for water. W stands for water, and that would be equal to 1 times 10 to the negative 14. Now if we took the log of all of that, we would end up with just the value of 14. And we can separate each one of these and basically say that the log of the ionization constant for the weak acid and the negative log of the ionization constant for the conjugate base is going to be equal to 14. Or we could just simply say the pKa and the pKb are going to be equal to 14. This is probably going to come in handy when you're doing your homework. When we think about buffering effectiveness, we need to take into consideration two characteristics of buffers. One is the capacity, and the other one is effective pH range. Now, a good buffer should be able to neutralize a fair amount of an acid or a base that you're adding to the solution. However, there's going to be a limit, and once all the buffering solution has been exhausted by however much acid or base you added, now you're going to start to see those shifts in the pH. Now, the buffering range is going to be the pH range at which the buffer can be effective, and this is part of the characteristic of the type of buffer that you're using. Some work better in a slightly acidic situation, and some work better in a slightly alkaline situation. The buffering capacity is the amount of acid or base that a buffer can neutralize. And again, that's going to depend upon the concentration of your buffer present in your solution. So basically we could say the effectiveness of a buffer is going to depend upon the relative amounts of the acid or the base that gets added to it and the absolute concentrations of the acid or base that get added to it. When we look at the buffering range, a buffer is going to be most effective when the ratio of base and acid is somewhere between 0.1, greater than 0.1, or less than 10. And we can prove this to ourselves by using the Henderson-Hasselbalch equation and substituting these two end range values. So we could calculate the pH here, and for our lowest pH we would substitute that 0.1, and we would see that the pH that this particular buffer would work at best this pH, or the low end of this pH, would be when we have that power of the dissociation constant of our buffer less 1. And then the upper end is going to be when we plug in 10 into our log and get this value right here, where we have the upper end of the pH effectiveness is going to be the power of the dissociation constant plus 1. So therefore, we can say the effective pH range of a buffer is the power of the acid dissociation constant plus or minus 1. So when choosing an acid to make a buffer, you have to choose one whose power of the acid dissociation constant is going to be closest to the pH of the buffer that you're trying to make. So a buffer is going to be most effective when the concentration of the acid and base, the ratios, approach 1, which basically means that we're looking at equal concentrations of our acid and our base. And the buffer is going to be effective when the concentration ratio is between this 0.1 and 10, as we just saw on the previous slide. A buffer will also be most effective when the concentration of the acid and the concentration of the base are large. So let's see what we mean when we make that statement. So the concentrated buffer is going to be able to neutralize more of the added acid or base than a dilute one. And the reason why is that we have more of our buffering molecules present to interact with whatever it is we're going to add to our solution. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different molecules that our acid or base, or added acid or base, can interact with. And over here in the dilute buffer, we only have 1, 2, 3, 4. So we have 4 interactions, and then this one's done. And whatever else you add here is just going to remain the acid or the base, and there'll be no further neutralization. Here you can continue to add, and you'll still have a little bit more life left in your buffering solution. Now, the buffering capacity is the amount of acid or base that can be added to a buffer without causing that large shift in pH. That's what we're trying to avoid. The buffering capacity can increase with increasing absolute concentration of the buffering components. That's what we saw on the previous slide. And as the acid-base ratio approaches 1, the ability of the buffer to neutralize more added acid and base actually improves. So the closer we are to that ratio being equal to 1, the better we are. Buffers that need to work mainly with added acid generally have the scenario where the concentration of the base is greater than the acid. And the opposite is true for buffers that need to work mostly on a base, an added base. They're going to have more greater concentration of their acid components than they are of their base components.